All right, so let's get started. Today we're talking about the LIGO, and we're going to be estimating some of the values that LIGO measured for two black holes colliding. So can you guys see my screen right now? Is it sharing correctly? And let's see, hopefully you can hear this too. All right, were you guys able to hear? There was a sound there. It was kind of like a chirp. All right, so that's the sound of two black holes colliding. And let me move this down here. What we saw is an event that happened a long time ago, but that event created gravitational waves that we were able to measure on Earth. And it was a collision between two stars. So let's start with the presentation. And you can see my screen now, I hope. And this is the LIGO discovery. So it happened in 2015, 100 years after Einstein had proposed that gravitational waves should exist. It took 100 years for a huge experimental collaboration for people to observe these gravitational waves. Almost 100 years. So what happened then is that with LIGO, is the name of the collaboration, we have now a new window to see the universe. So the first thing is that the LIGO observation, this is the name of this two groups, huge groups of people. They had to make the most sensitive measurements ever made in the history of science. And we're going to talk about that today. It created a lot of interest. How many of you have heard of this experiment? All right, so about 2/3 haven't heard of it. A little bit more than 2/3. So it was, sorry, I don't want to do that. How do I make this small? All right, let's put it down here. So it was an event that consisted of the merger of two black holes. The data that you heard and you saw on the screen is what the data that was measured. So for instance, here we have two black holes. This is what this cartoon is about. And the two black holes are orbiting each other. So it took place billions of light years from here. So that means that this gravitational wave has been traveling for 1 billion years or more to get to us. And then the data tells us a lot about what happened. So let's look at the data. So this is a cartoon of it, and this is some data coming out of this. But the actual data looks like this. So here we see, this is the figure that they say, that they have. In this particular article, Observation of Gravitational Waves from a Binary Black Hole Merger, published in 2016, what you see on the top left is the strain. And you guys are familiar with strain. So for instance, if you have a bar and you push on it, you're putting a strain on it. If you pull on it, you're putting a strain on it, right? So here we see on the top left of the panel, we see the strain observed in the Hanford, Washington Observatory as a function of time. So here is time. It took half a second, and you see this strain on it. So that's the top left panel. Then the top right panel over here, this one is the same thing, the data for the Livingston detector in Louisiana, but it's overlaid with the one in Washington. So this is the red data is overlaid right here, and then they shifted a little bit to account for the gravitational wave. So the gravitational wave is passing through the Earth, right? So Washington is over here, the state of Washington is over here, Louisiana is over here. It reaches one first, and then because of the speed of light not being infinite, it reaches the other one. So then they shifted the signal a little bit, and they were able to see how well they match. And you don't see it as well over here, but you can tell exactly how amazing this match is in this portion of it. There's an excellent match between the two detectors. So what happens is that you have a system in Washington, and then you have another one in Louisiana, and both of them measure the same signal. I told you that this is the most sensitive system ever measure to look at how something changes in length. And what happens is that as the gravitational wave is passing by, it contracts the space a little bit or expands it in the other direction because the gravitational wave is doing this to space. And that's actually what this signal is that we're seeing here. So we see that the strain in 10 to the negative 21, this is the units of it. And what that amounts to is that they were able to measure, with that sensitivity means that they were able to measure something getting pushed in by a millionth of the width of a proton, a millionth of it. So that's how sensitive it was. So they have made it so that the detectors, if they had seen some noise in only one of them, then it could have been because somebody was passing near the detector and that made things vibrate. But because they see the same data in both ends of the continental US, then you can tell that you have something that passed through the whole Earth, not just that somebody was driving by in Washington or in Louisiana. So the next two datas are basically that they're looking at, they put a filter on to remove some of the noisiness up here. They put a filter on that. And then what you see here is the data in gray. And then in red, you see what the numerical relativity would be, the simulations using general relativity computers to solve the equations of general relativity for those two events. And you see how well they match to the data in gray, the reconstruction of the data after it was filtered to remove some of the noise. So the third data is called the residuals, and that's just subtracting one value from the fit in the first row. And you see that it's not that big. It's just a tiny amount for those residuals. So that would be kind of like your error. And then the last one is the one that we heard just a few seconds ago, where you see that you have as a function of time, this is what frequency was present on the signal. And it was low frequency sound. And then all of a sudden it got to go up. So that's the chirp that you heard. There was whoop. That's because the frequency is going up. Questions so far? Or anything that is not explained that you would like to hear more about? All right, so then I don't see anybody raising their hand or asking questions. Let's talk about what we're gonna do today. We're gonna use Newtonian gravity. Even though Newtonian gravity doesn't give you the answer to a lot of stuff, I'll let you know when it's not applying, but basically we're gonna use very simple Newtonian physics 2014. And then something that you probably won't get a chance to cover from E&M, but actually applies both in E&M and in gravitational waves, because electromagnetic radiation and gravitational radiation, they're both waves. So the math is the same. We're gonna look at two black holes, how they merge and what would we observe from doing that. And that's what we're doing. So some parameter estimation. All right, so let's start with Kepler's third law. This is something that maybe you don't remember, but maybe you do. So we have, let's see. That didn't look good. So let's say that we had a black hole here and another black hole here. And they're orbiting each other. So basically, if they're the same size, their center of mass would be right through the middle, right? So we have two black holes. Let me make one be mass big M, and the other one is mass little m. They have a common center of mass. If they were the same mass, the orbit, let's assume, is circular. And if they're the same mass, then the center of the circle will tell you where the center of mass of the two objects is. However, if they're not the same mass, then the distance from this point, the center of mass, to this little m is not the same as the distance from one to the other. So let me make this one here. We'll call this radius r. And then this one from here to here, little r. Again, if they're the same mass, they would be separated exactly the same. But what we see is that they're orbiting each other, and they're orbiting, each other are orbiting the center of mass. And they're separated at distance r, capital R and lowercase r. And they're on opposite sides of the center of mass. And they have a frequency at which they're orbiting, right? So this would be the angular frequency. And you guys are starting to have flashbacks to 2114, right? This kind of problem you have seen already. So now, something that you already know, again from 2114, is that the mass big M times little r is equal to the little m big R. At least initially, when the two black holes are far away, they're gonna behave like this. They're well separated, and then this is just, they're working through Newtonian mechanics. So you have the Newton's law of gravity applies. So now, if you use Kepler's third law, you can figure out, you could derive it, but I'm not gonna ask you to do that. You could derive it from your physics 2014, it's probably in your book too. But we can figure out what is how the angular frequency is related to the separation of the two black holes. And what we would end up with is this omega squared is equal to, and here is capital G, and then on the top is little m plus big M. And on the bottom would be little r plus big R cubed. So this is one of Kepler's third law. One way to write Kepler's third law. So we're assuming that the orbit is circular, so that we can write it as simple as this. If it was elliptical, the equations are more complicated, but it turns out that even if it was elliptical, having the elliptical form, when they start orbiting each other, they're going to emit gravitational radiation. And then because they're emitting gravitational radiation, it turns out that this elliptical orbits is not as good. So they start doing circular orbits. Any questions so far? All right, so then let's talk about orbital energy. Again, this is what you would be able to get from your Physics 1 class. We want to calculate and estimate the total energy of the system. And what we have is the kinetic energy of the system of both black holes orbiting, right? And then the orbital energy is that from orbiting. And we would end up with this equation. This is the potential energy from orbiting around that center of mass. So this gives us the energy of the system as a function of the black hole separation. So you can see that here, this is basically the distance between the two. That's the parameter that we have there. And we also see that here, this is related over here. So we could graph the equation on the top from Kepler's third law and substitute it in here. So we could solve for R plus capital R, right, from omega, and stick omega instead of R capital R over here. So if you do all of those calculations, this is just algebra. Using Kepler's third law, I can get that the total energy of the two objects orbiting, this stays the same, but now since there's a G over here, and I'm gonna take this equation over here and try to fit it down here, some things get modified, and we have 2/3 G, capital M, little m, capital M plus little m, 1/3 down here, and then 2/3 for the frequency. So that's from grabbing this equation, solving for the R plus R, little r plus big R, and writing that out over here and doing all of the simplification of the algebra. Questions?
Can you repeat again how you got to how we simplified?
How do I go from this equation? From this equation?
What did you plug where?
Yeah, so I grabbed so I don't know if you see my mouse. You see my mouse?
Yes.
All right. So what I did is that I know that this omega squared is related to the R plus R, right? And I want to rewrite omega squared in R plus. So I want to solve for what is R plus R from this equation. And then I just sub that in here. So if you look at this one, right? Like for instance, if I have that I do this, let me see. So I have on this end omega squared, but if I go 1/3 over here, then what I would get is G 1/3 and then capital M, little m 1/3 down here. I would get R plus big R. And then I keep just doing algebra. So now I can multiply R plus R on this end and put it. So I would get R plus R is equal to, then this one goes on the bottom. No, hold on. What am I doing? Yeah, no, not like that. Let's not skip steps. So from there, I could write R plus R. And then here is omega to the 2/3. And then is equal to G 1/3 and then the M plus M 1/3. And then I just have that R plus R is equal to G 1/3 M big M 1/3 and omega 2/3 on the bottom. And then I stick this R plus R in this equation down here and then just see what things cancel out. So I have a G over here and then there's a G down here, 1/3 of it cancels out. And then this one and this one don't cancel out, they just get written right there. So this is this term, and then this term is this term, and then this one is just this one. So the algebra works out like that. Is that clear?
Yes, thank you.
All right. So we have calculated certain things. Now, the next thing is gravitational radiation emission. So one thing that I have to disclose about this, when you're looking at Newtonian physics in the Newtonian framework, gravitational radiation from a circular orbit doesn't exist. So here we have a circular orbit, those things are orbiting each other. Newton's gravity equations don't lead to any radiation emission. However, that's not correct. And Einstein solved this in 1913 maybe. What he did is with general relativity is that he saw that the equations of orbiting two black holes are gonna be emitting gravitational radiation. And because they're emitting gravitational radiation, right, that some of that energy that they have because they're orbiting each other gets emitted. And we see that radiation is energy being lost away and that two objects start moving closer and closer together. So his prediction was that if you had two black holes orbiting each other, they were going to emit radiation, gravitational radiation, and they were going to be losing energy. And because they're losing energy, they're orbiting closer and closer together. And then all of a sudden, they're going to spiral into each other. Gravitational radiation is produced by these large objects moving around themselves. So this is the same idea that you get when you have charges moving. So I don't know if you guys covered this. When you have a charge accelerated, they produce radiation from E&M, right? That you should cover. Now, if you had two charges orbiting each other, you have, and I don't think that you have time to cover that in 2114, but if you have two charges orbiting each other like this, you can look at how the electric dipole moment of that charge distribution changes. And you can see that because they're orbiting each other, they're gonna produce electromagnetic radiation. So this is the exact same thing, analogous to the electromagnetic dipole radiation that you would see, and that the field that it generates can be solved for. So the energy in a gravitational wave is pretty much like the energy density in an electromagnetic wave. And in electromagnetic waves, what you do is that you square the electric and magnetic field to get this radiated power. And it turns out that so in E&M, this is proportional to the square of the electric field and the magnetic field, right? For gravitational waves, we have that the emitted radiation is actually given by some constant. This is a constant that at this point we don't know. The gravitational constant has to go there. Then the moment of inertia of the system, oops, sorry. Then the frequency to the sixth power, and then the speed of light. So we have a system where you have these two orbiting each other with a center of mass, and we actually can write what is the moment of inertia. This is also one that you did before. In this case, it's just the two masses on the top multiplied together, that two masses added together on the bottom, and then the distance between them is squared. So you guys remember this one, right? So thing to notice, as the two black holes start orbiting each other, they're going to emit radiation, and then this distance is going to get smaller. So their moment of inertia changes too with time. So it's not a constant. All right, questions so far? So the only one that we cannot get from Newtonian physics is this guy. This constant, you do need general relativity. And general relativity tells us that this is equal to close to this value. Any questions? All right, so then what I'm gonna do is just grab this equation right here and start putting things that we know. So we know, at this point, we know this one and this one, right? From the previous equation and this one. So if I do all the algebra, we have that the emission, the radiation emission, the gravitational emission is that thing that I didn't know what it was. Then the G's become 7/3. My frequency, because there's a frequency before, becomes 10/3. Then I have the c to the 5 right here, and then I have to multiply by the moment square. Two-thirds. So that's from doing the same of using this equation for r plus r over here. Okay? All right. Questions? No? All right, so then another thing that we can look at is the Schwarzschild radius. So the Schwarzschild radius, or the event horizon of the black hole, is the distance from the center of this spherical body of mass. What is the escape velocity? And if you have a gravitational body, you would get that is 2gm/r, right? So this is again physics one. In this case, it's assuming that r is greater than the radius of the spherical body, right? So if you have a planet right here and you want to have that, you're going to put your rocket right here, how fast does it have to move? It has to have that escape velocity, otherwise it's just going to fall down on Earth. So if we set the escape velocity to the speed of light, then we can figure out what is the radius, and this is the Schwarzschild radius for an object that escape velocity needs to be the speed of light. And that becomes 2gm/c². So if we know the mass of the object, we can figure out what is the Schwarzschild radius. For a very dense object, then it can be that the event horizon is this distance, the Schwarzschild radius, and it tells you what is the size of the sphere or radius. This radius tells you the size of the sphere that surrounds the black hole. We actually don't know how big the black hole is, but we know we can estimate based on the mass that there's a distance at which nothing can escape it. So we call that the event horizon. Light can only escape from the black hole if it's outside of the event horizon. So we can assume that we could even assume that the black hole is a point singularity, just a little point with all of that mass in it, but it would have these event horizons anyways. All right. So here's the first thing we're going to estimate. Let's assume first that we have the two black holes and that they're going to start to coalesce, to join together once their separation is equal to the sum of their Schwarzschild radius, right? So that means that the first one has a radius of r, the one that is mass big M, and the other one has a little mass r. So this is when the two black holes collide. So that's just the distance. And we can figure out what would be this escape velocity, and we would have this thing and this two masses. That's the separation here according to that angular frequency that we have over here. We can rewrite it and put it in there. So we can figure out what is the actual angular frequency of the two black holes. So we actually can have that if they're separated by that much, they're orbiting each other. And we have that this is the maximum frequency that they're orbiting against each other. Okay, so now this is the angular frequency. And this angular frequency is when they're colliding. So what we have is that, let me put it up here. The actual frequency is just omega c over pi. Okay, that's the highest frequency that we would see. All right, any questions? Let's look at this thing over here. You guys see this, right? At this point, right here, that's the highest frequency that we see. What is that frequency? Anybody? So what is this value of the frequency at this point? Let's see, Jared. Arthur?
I'm gonna,
Estimate this number, right?
what?
Estimate this number. What do you think the number is here for this frequency?
Maybe around 300.
Excellent. So big round number, right? So this is 300 hertz. All right. So this is what your homework is going to be. We see this equation right here. So now we know that I know that, so this is 300. So I know that this is related to 300 by multiplying 300 by pi. You know the value of the gravitational constant, and you know the speed of light, and you know the units for it, right? If we know those two values, what is the combined mass of the two objects? If we use the 300 value, what is the combined mass? Should I do the algebra for this one? So let me write this out. This is your first question for you guys. And is question 1. Estimate big M plus little m. So let's go over this equation over here, right? So we know on one end is this function over here. And this is the equation that you would be using. The total mass of the big object once the two crash together is given by little m and big M. And just looking at this previous equation that I have here, okay, this one right here, I'm solving for the two m's together in terms of the other constants. And using the pi value to have the actual frequency, you have this equation. Oops. FC, where FC is 300 hertz. Okay, so that's the question for you guys to solve. Any questions? Yes, no? Is it clear what your job is? Sivan, any questions? All right. Yeah, exactly. You're just plugging everything in and looking at what value you get for the mass of the two. Oh, this is something I want you guys to use as the two masses. Converted whatever mass you get converted to solar masses. So for instance, you know that the mass is the sun of the sun is given by some value, right? That's the mass of the sun. Just put it in units of the mass of the sun. Okay? And that's all you have to do for this. All right. If you don't have any questions, then that's all I have for today. And I'll see you next week. Thank you very much.